I can guess. Otherwise, because these two characters, Zixuan, typically corresponds to like the meaning. There's a meaning of the word. So yes, I will announce that. So I will just and so colleague. So we.
Okay. I see.
I see. Gotcha. All right. I suggest that we start with the morning session. This morning we have a little bit of a continuation of yesterday's topic, dwarf galaxies. And we will also cover new topics specific to this morning, feedback and star formation. We'll have 4 talks before the poster session. Our first talk is by Zixuan Peng from Santa Barbara. He will be telling us about the physical origins of outflowing cold clouds in local star-forming dwarf galaxies. Welcome.
Thanks so much for the introduction. Hello, I'm Zixuan. I'm a fourth-year grad student at UC Santa Barbara. It's really my honor to give a talk here. I really appreciate the opportunity. I think among this discussion section, we kind of reached the consensus that our understanding of AGN feedback is kind of limited. And today I'll try to argue that our understanding of supernova-driven galactic outflow and galactic ring is probably also quite incomplete. For example, the mass, momentum, energy alpha rate derived from emission and absorption line, they are both quite uncertain with large uncertainties, and they usually do not agree with each other. So to address those challenges, I would suggest we should better compare observations with series, and that was exactly the motivation behind our project I'm going to present today. So I just want to give a brief summary of the physics of superbubble expansion and blowout. We know that end stage of massive star cold-class supernovae will eject tremendous amount of mass and energy to the surrounding interstellar median and power an expanding superbubble. And this superbubble is initially energy-driven, where radial cooling is not very strong, and then it will transition to a phase where the shock interstellar median gas has been collapsed into a thin shell, and this thin shell will begin to fragment and maybe due to radiator instability and starting to form the superbubble blowout. And subsequently, then we can form this kind of a galactic scale outflow and galactic ring like we typically see, for example, in M82. And the galactic ring is multi-phase. We can trace this half phase, for example, through the X-ray data around 10 to the 6 to 10 to the 7K. We can also trace this cold phase around 10 to the 4K using optical emission line and also UV absorption lines. So to trace these outflows, multi-component analysis is the key. For example, in the cold phase, people usually use the blue shifted component in the UV absorption line and also the broad component in optical emission line to trace galactic outflows. So an intuitive follow-up question would be that what are the physical regions of these outflowing components? For example, all of these components are chasing galactic ring that can escape from the gravitational potential well, or they can also chase, for example, expanding superbubble shells. So to answer that, we leverage on the Class C survey, which is an ideal example for us because that Class C contains of 45 local UV bright star-forming galaxies that spans a wide range of physical properties. For example, in stellar mass from 10 to the 6 to 10 to the 10 solar, and the gas phase metallicity from about 5% to 100% solar. And in our previous study, we target at 14 Class C galaxies using the CAC HLS spectrograph and imager. And from our rigorous multi-component analysis, we found that 13 out of 14 Class C galaxies need a triple component fitting in comparison to the most of the literature study that only found 2. And to classify these velocity components, especially in O3 and H alpha, these strong emission lines, then we can base on their UC-HiPACC and their relative contribution to the total flux. For example, for the narrow component, their fluid half max is only around 100 km per second, and they have the largest contribution to the total flux. But for the very broad component here, they are very extreme. They can up to 1,200 km per second. And I want to emphasize here, this is star-forming galaxies. It's not type 1 AGN. And so people might wonder, like, if broad and very broad component, they all chase galactic outflows, then what are their physical regions? Are they chase the same gas? To gain more insights on that, we can plot some outflow properties versus some global galaxy observed load. For example, here we are plotting the maximum velocity versus star formation rate for the broad component showing as the open markers versus the very broad component showing as the solid markers. And as you can see, they lie in a very different regime and may indicate they have very different physical regions. For the broad component, we found that their scatter can actually be explained by superbubble models with different bubble expansion time and ambient densities. In contrast, the scatter of the very broad component can be actually explained by galactic ring models with different mass loading factors. So based on our analysis here, we are trying to argue that broad component is tracing the expanding superbubble shells, whereas like the very broad component is actually tracing the fast outflowing galactic ring that can escape from the gravitational potential well, and they are formed from the blowout of these shells. So you might say, like, you're only based on 14 galaxy sample. So in our preparation work, we actually expand our sample size to 27 classic galaxy using both ESI and KCII measurement. And this is just integrated spectrum. Qualitatively, we reach very similar results. But here I want to emphasize, for the broad component, their scaling relation are going to converge to the UV for the measurement based on UV absorption lines. So they might indicate that UV absorption line might chase a similar physical region as the broad component in optical emission lines, but they have a slightly higher Vmax. So this is probably because of their different density dependence for the absorption and emission line. We know that for the absorption line, it is linearly dependent on density, but for the emission line, it is dependent on density squared. So emission might chase a denser gas compared to absorption line, so they have a slightly slower outflow velocities. And we also have done some spatial result study using both ESI and KCII observations. Due to the time constraint, here I'm just showing one of our examples using KCRM. And here the green aperture represents our field of view, and the red contour here shows the region that we actually need a triple component fitting. And if you extract the 1D spectrum from them, you can see that all of them have a very broad rings, and these very broad components, their fluid half max is usually larger than 1,000 km per second, and they are very spatially extended. So definitely they are not type 1 AGN. And if we have this surface brightness measurement for both O3 and H alpha, then we can measure their O3 to H alpha surface brightness ratio spatially, and then we develop an analytical tool to predict the emission line surface brightness based on both single phase and multi-phase model. And you can see that here, I want to emphasize multi-phase model can better reproduce the very broad components O3 to H alpha ratio in comparison to the single phase model. So this multi-phase model incorporates the turbulent radiative mixing between the cold cloud and the hot phase. So it's further proof our argument that very broad component trades a cold cloud in train within the hot ring. So if you're interested in this model and their application, I would love to discuss more with you during the coffee break. And so right now we know that galactic rings are multi-phase, definitely, but we still do not constrain the cold phase mass and energy alpha rate really well. One of the reasons is that the thermalization efficiency factor and the mass loading factor, which controlled the energy and mass input rates of the hot phase, they are really highly uncertain. They are not constrained by both observation and series. But if we assume that the cold clouds that traced by the very broad component is in pressure confined by the volume filling hot ring traced by the X-ray, then we expect the square root of these two products of the very broad component should be very similar to the X-ray data. So leverage on our KCII observation, we can spatially derive the mass alpha rate and the energy alpha rate to determine the total mass loading factor and the thermalization efficiency factor. And when we compare the measurement for the very broad component, we found that they are consistent with the actuator's constraint in the literature. And also here I want to emphasize for one of the targets here that we have like the eta-E and eta-M measurements for from both emission and absorption line. As you can see, the X-rays value is very similar to the value of the very broad component, but they are very different from the value derived from UV absorption line. So here again, I'm to emphasize here, like the very broad component should be the one that traces the fast outflowing galactic wind. So for the last part of my talk, I want to emphasize of a very unique target, SBS 0335. It's a very metal-poor dwarf galaxy in the local universe that we find a very interesting explanation for its broad wings. And I just want to give a very brief summary of this galaxy. This galaxy has been considered a starburst galaxy in the last decades. As you can see, you can clearly see these supernova-driven shells from the H-alpha narrowband image. 2 years ago, a paper from the Masami Oshi's group claimed that they found an active black hole, massive black hole, at the superstar cluster 1 and 2 here. And their argument is primarily based on the near-infrared variability in the W1 and W2 bands, and they also find that there are some detected neon-5 emission in these superstar clusters. And also, they found that the broad wings in Balmer lines, for example, H-alpha, can be up to 10,000 kilometers per second. And based on our recent cases of Y, cases of iron observation, we think this AGN interpretation is kind of questionable because we found that in the forbidden O3 507 emissions, we also find very broad wings. So in typical type 1 AGN environment, we know that like the density is so high, much higher than the critical density of O3, so usually we'll collisionally de-excite O3, so you not like expect any broad wings in the forbidden O3 lines. So we are trying to find an alternative explanation for these superstar clusters. So we argue that superstar clusters 1 and 2 should exhibit luminous blue variable or LBV candidates very similar to Eta Carina. And the black hole-like signature we just saw can be explained during an LBV outburst phase. And so the LBV outburst phase is just a very strong mass loss phase. For example, during the 1840s, a giant eruption of Eta Carina, it can last up to 10 solar mass in a very short time. And people argue that the LBV outburst is due to the binary interactions of the LBV star and the secondary companion star during their periastron. So due to time constraint, I'm going to focus on how the LBV picture are going to explain the very broad wings we see in H-alpha. So if you zoom in around, so before the giant eruption, we also, the pre-stellar mass, the pre-stellar wing material will form a second stellar median around the binary system, which is shown as the bipolar shape nebular emission. And if you zoom in around this second stellar median, you can see that it is optically thick and it is radio expanding. So basically, the photon generated within the second stellar median need multiple scattering to escape from the outer boundary. And with the increasing number of scattering between photons and electrons, then the photon frequency will gradually deviate from the central frequency and potentially contributing to the very broad wings we see. And also, because the photon frequency is redshifted in general due to the non-radial scatter between the photon and scatter. And we can see that our proposed electron scattering model with an optical depth of 10 and with a certain radial expansion velocity of the second stellar median can explain the broad wings we see in H-alpha really well. So I'm trying to argue here the very broad H-alpha wing we see in this target is not due to the broadline region in a type 1 AGN, but instead due to electron scattering within an optically thick and the radial expanding second stellar median. So I think I'm just going to leave my summary slides here, and I'm happy to take any questions. Thanks so much.
This is amazing. Thank you.
Yep.
So you showed that you can measure energy loading factors
Yeah.
from the data. Can you clarify how you do that? And what are the typical uncertainties?
So basically, like you can measure the H alpha luminosity from the very broad components that we think that trace the cold clouds in train with the hot winds, and then we can derive the mass alpha rate, and then from that we also know the from the velocity from the very broad component, then we can derive the energy loading factors. But we need to assume, for example, a certain energy input rate from the cold cloud supernovae.
Okay, we have time for another question while Jenny can set up.
Yes. With regard to the estimates of the total energy, do you have to adopt some inclination? Because otherwise you don't know the transfer of the velocities that you see to the actual velocities. How do you make the inclination correction? Do you adopt some procedure for getting the tilt of the biconical structure?
So do you mean like the maximum velocity we measure, like you need to correct from geometric? Yeah. So if you like, so for most of the, I would say like for a negligible, non-negligible fraction of a target, they have a very like large orbiting angle for the bicom. So basically you can, if you assume that this is a spherical system, then the maximum velocity is like basically the same as, yeah. Yeah. Okay. Yeah. Thanks so much.
Only if it's really quick.
Some people have suggested that you can test this by looking at different CAS lines, that they should show similar scattering. Can you comment on this?
Yeah, I think so. When we first see these targets, we think there's a high density CSM because like we can use the iron 2 lines ratio because iron 2 traces the partially ionized zone, and we use the iron 2 line ratio and we trace like in the partially ionized zone the density is very high, like up to 10 to the 6. So if you want to find a similar system like this, we probably need to use some iron 2 line ratio, or like using some, for example, O1A446, which is the Lyman beta boron fluorescent line, to see if there are any like similar high density systems, and also this system should be like extremely young. Yeah.
Jenny, please connect now.
So in one of your first slides, you showed Vmax, where the star formation rate.
Yeah.
And what I found fascinating is that Vmax decreases for the fast component with increasing star formation rate. Naively, I would expect the opposite because you have more energy input, so you would expect more acceleration, but it's just the opposite. So why? Why is it so?
Yeah, I think so. From galactic wing model, you expect like the Vmax does not depend on star formation rate. And we found that the scatter of the very broad component in the Vmax versus star formation rate space can be explained by different mass loading factors. So I think it is the negative correlation we see is I think it's basically due to like we have like less sample on the low star formation rate end. And if we include more sample at that end, I think we can find a relatively flat correlation. Yeah.
Okay, let's thank our speaker again.
Yeah. Thanks so much.